Hello beautiful people, welcome and welcome back to the channel. Welcome to our applied mechanics lessons. I hope you're all doing well today. On today's lesson or video we will be tackling friction, and today's example specifically will be friction if your object is at an incline, or if your surface is not completely horizontal, if it is at an incline. So the question reads as follows: a body with a mass 100 kg, so 100 kg, rests on an inclined plane at an angle of 15 degrees to the horizontal. Calculate the force at an upward angle of 20 degrees to the inclined plane, which will A, pull the body up the incline, B, pull the body down the incline. Okay, so there are some important factors that we need to take into account here. So now we need to look at the information that we're given and then try and relay it to a diagram, because remember, your diagrams count for marks as well. Your diagrams are not just there for fun, right? So first of all, we're told that the surface is inclined at 15 degrees to the horizontal. So we have, that's horizontal, and that'll be a 15-degree inclined surface on there. Okay, let's just not make it look dodgy. I hope it's not dodgy. We don't want it to be dodgy. Okay, perfect. Then we can add our object on here, and we're told that it has a mass of 100 kgs. Okay, that's the mass that we have, and the question comes in two parts. Part A needs you to calculate the force at an upward angle of 20 degrees to the incline that will A, pull the body up the incline, and B, pull the body down the incline. So we can have two simultaneous diagrams just so we see how to apply the difference on there, right? So this will be the second one, still has that angle of 15 degrees, and we have our body on there. It's still 100 kgs. Okay, so the very first scenario on here, let's focus on the very first one. We're told about an upward angle of 20 degrees. So this force is at 20 degrees to the incline. All right, that's the force F. That is essentially trying to pull the body in that direction. It's trying to pull it up the incline. But remember that with whatever direction your force is moving in, you have an equal and opposite frictional force that is essentially trying to keep the body in the same position. But because of the incline, we can just put it on here. That's our F mu. That's our frictional force that will keep it in the same position. And then now that we have a force that is at an angle, that automatically tells us that we need to express it in terms of its perpendicular and parallel components. So we won't get into components. If components still don't make sense at this point, I highly recommend that you refer to our components video, which I'll attach a timestamp to right up here. It's right on the channel, so don't worry, you don't have to search for it elsewhere. So this becomes your F cos 20. This becomes your F sine 20. Okay, fine. Then we're moving on. Now we're moving on, and that's about all. Remember, the very first important thing, or the most vital part of this whole entire exercise, is you figuring out the forces that are acting on this whole entire system, what direction they're working in, as well as how you can try your level best to express those forces, right? So remember, directly perpendicular to the surface, to the flat horizontal, we will have your mgn here. That will be the force as a result of the weight of the body and the gravitational pull on that. But there's something else happening. We haven't accounted for this inclined surface at an angle of 15 degrees. Okay, and that is what I'd like us to pay attention to right now, right? Normally, when you're doing your components, right, if you're at 15 degrees, this side would essentially be your something y sine of 15, and then the horizontal would normally be your x cos of 15. Okay, that's how it normally happens. But now there's an incline and there's a specific angle upwards of that incline, so it doesn't necessarily work in the same way. Okay. So I need to just explain what we mean by this, all right? So we have our incline of 15 degrees, and the components that we will be expressing will be components that are a result of the body that is at an incline, not necessarily the components of the incline to the horizontal surface. I don't know if this makes sense. I really hope it makes sense, right? But if you look at this scenario here, we have a triangle that's going completely down that represents your MGN on there, and then this triangle forms essentially an angle. Let me use a different color, an angle theta on there. Then already from this system we already have an angle here, we have an angle there, and we have an angle here as well. Okay, now we'll essentially try to represent this line in terms of our MGN. We're not trying to represent it in terms of the horizontal line that is there. Okay, so we're now trying to take into account this triangle over here. So our hypotenuse will essentially be our MGN, and then, okay, I messed it up. I messed it all up. Let's try this again. Okay, so that is essentially your MGN. It's going straight down. There's an angle on here, and that is a 90-degree on there. And then there's an angle on here. You'll choose whether to involve it or not. But the reason why I'm choosing to show you this diagram is so that we pay attention to the angle or the included angle that we are working with. Okay, so here we have our hypotenuse as mg that I've already mentioned, and then we will be using the included angle of theta on there. Then what we need to express is essentially this, which will be your opposite side, and this, which will essentially be your adjacent side. Okay, the reason why we need to now essentially find a way to, wait, I'm lying, it's not, sorry, this side is adjacent to that angle there. That's the angle we're trying to use. This side will then be opposite to this angle. Okay, I'm confusing myself with all of this talk about hypotenuses and stuff. Now, the reason why it's important to know the angle you're using, your included angle, it helps you identify which side is opposite, which side is adjacent. And you remember from our SOHCAHTOA rules, wherever you have your adjacent side, that's where you'll have your cos. Wherever you have your opposite side, that's where you'll have your sine. You'll have your something something sine. Now remember, we're now expressing everything in terms of our mg, so this will become our mg sine of theta. Pay attention to the direction. It is essentially moving parallel to the surface. Okay, then similarly this one will become our mg cos of theta. Pay attention to the direction. It is moving perpendicular to the surface, perpendicular to the inclined surface, not to the horizontal surface. The reason I'm showing you all this mushy, all of these details, is the fact that we're not done with expressing our forces on here after showing our mg, our f mu, and our f, and showing its components. We now need to account for the surface that is at an incline on there. So now we need to show essentially a force that's perpendicular to the inclined surface. It will be on here. That's one of the components, and then there will be a similar component on here that is running parallel to the surface. Now going back to this, remember that this was at an adjacent, so this will become mg cos of 15. Then this one will become mg sine of 15. Okay, similar to this one over here. We can fill out the forces, so by the time we calculate it doesn't get confusing, right? So we, at point B or question B, we are looking for a force that will pull the body down the incline. It is still at an upward angle of 20 degrees. So it's still there, 20 degrees, and we still need to show its components. So that will be F. Okay, this B is just taking up space for no reason. We C uses it TNZ, there's no need. That will be F cos of 20. That becomes F sine of 20. And because it's trying to move the body in that direction, it means your frictional force will be in the opposite direction, right? But we're not done. We're not done expressing the forces. We need to show our gravitational pull, which goes perpendicular to the horizontal. That's your MGN. And then perpendicular to your inclined surface, you have your mg cos 50. Then perpendicular or parallel, to your inclined surface, you have your mg sine 15. Okay, now let's pay attention to how everything moved. Actually, this should be facing the other direction. Should be facing the other direction. My components are dizzy, so let's move the force of resistance this side, because we've already identified that's where it will be moving to. Then we'll have our mg sine 15 on here. Okay, then just to recap on the forces that are acting on our diagram on here, we'll have the force that's trying to act on the body, trying to force the body to move, and then we have expressed it in terms of components here and there. Then we have the gravitational force on here. Then we needed components to express the relationship between the body, the inclined surface, as well as the horizontal. So that's essentially what those are. Okay, then now we can start with our calculations. I'm just gonna get rid of this here because we will need quite a bit of space to solve that. All right, then on here we can assume a coefficient of friction of, should we say 0.4, 0.25, 0.5? Let's say 0.4. Let's try a coefficient of friction of 0.4. Then we're now starting with part A. We're trying to pull the body up. So remember, we normally equate it in this way. We say the forces that are the forces applied on the body, forces applied, we equate them to forces that are resisting that. Okay, so these ones are trying to pull it up, and then these ones are trying to keep it still. Okay, sharp. So the forces that are acting on the body, that's the force F we're trying to come up with. Forces that are resisting are your frictional forces. Okay, then remember we have an equation that your frictional force is equals to perpendicular forces times your coefficient of friction. All right, then on here we're gonna look back at our diagram. Okay, so this, I normally call it F at X or Fy and Fx, just so it's easier for me to kind of label it, right? So the forces acting on the body, there's a force that is trying to pull the body up. It's trying to move it. And whatever force that you come up with, do not confuse it with the forces that are acting perpendicular to the body, because those are the forces that will essentially be working together or against the weight to keep the body where it is, or to reduce the amount of friction that's acting on the body. Okay, so when we say forces, that is force that is applied on the body or force that's trying to pull it up, we are going to pay attention to this F cos of 30. Okay, please make sure this portion doesn't get confusing, because you miss it here, you are out, my sweetie. You are completely out. Okay, are we still together? We are. Then we're going to look again. This force is moving to the right. We already know that this force is already expressed in terms of the perpendicular forces and the coefficient of friction. We don't have to pay attention to it. And then when we look, could there be any other force that is acting parallel to the surface that may or may not be working with the force that's trying to pull it up? What I mean is, if we have a body on here, we have a surface, something is pulling it there, something is pulling it there. In as much as the goal is to get it in that direction, these two forces equally contribute to how this body will move. So when we go back to our diagram, we have our F cos of 30 that's moving to the right, and on this side we have our mg sine 15 that's moving to the left. The reason why we're now going to essentially consider it is because it is within the same plane. It's acting along the same plane as your fx. So on here we're gonna say minus mg sine 15. I feel like I could have written everything this side. I have a thing with my equal sign remaining in the same position. So F cos 20 minus, it still won't happen, will it? Mg sine 15, sharp. Then on here, we're trying to express our frictional force in terms of that. Now we are going to look at the forces that are acting perpendicular to our body, right? The very first obvious one is your F sine 20. It is your perpendicular component. So we have F sine 20. Okay. And then we're going to go back to our diagram. Right, you can decide which one you want to act upwards or downwards. Doesn't really change much. Okay. But normally what I do, I like to elect the gravitational one as the positive. That way, whatever force we have appointed, we are able to decide whether it's acting in the direction that we assumed or in the opposite direction. So we can here start off with our mg. Okay, that's our very first force, and it's going upwards. Then we have Alright, so we're moving on. So next we now need to consider forces that are acting perpendicular to our surface. Now on here, it's very easy to get confused because we had that mg, but remember, because our surface is inclined, there is no way where you will be expressing mg on its own. Your mg has now been expressed as the parallel component as well as the perpendicular component, right? So now we're looking at what's perpendicular to the surface. We've already taken into account the mg sine 15. So now we're going to come here, and our very first one will be our mg cos 15. It's going downwards, so we're assuming that downwards is positive. Then the opposite one is our F sine 20. Is there any other perpendicular force? No. Then we decide to multiply everything by our appointed coefficient of friction on there, right? I know my handwriting is getting a bit dodgy, but bear with me, okay? The next, we are essentially trying to get to a point where we will be able to have F as our subject of a formula, okay? So cos of 20, it's 0.9396. So we can say 0.94F minus sine 15 Wait. Okay. I see what happened here. We had a mass of 100 kg. We have a G of 9.81. Okay. And mg essentially gives you a force in newtons. So 100, can substitute it here. 100, 9.81, sine 15. It's important that you write down everything. You never know where you might pick up marks or where you might be losing marks. Okay? Then is equals to same thing, 100, 9.81 cos 15 minus, that one we can calculate right off the bat, 0.342f, and all of this is still multiplied by 0.4. Okay, it looks like it's getting longer and longer, but let's trust the process. Okay, so this we can keep it as is for now. 100 times 9.81 sine 15. This gives me 253.9. Okay, let's try it with the cos 15. It's on the opposite end. Okay, 947.573 minus 0.342f remains the same. Remember, this is still multiplied by 0.4. Okay, then you can essentially 0.4 times 947.573. This will be equals to 379.029 minus 0.342 times 0.4, 0.1368. It has 4 decimal places. I'm just going to add all of them just so it doesn't impact the answer we get right at the end. I don't like rounding off too much before we get to the very end. Okay, then what you can do, you can put all the f's on one side, put all the normal numbers on the other side, and then you'll proceed to solve it. So on here we could say 0. Why do my zeros look so dizzy? 0.94f plus 0.1368f is equals to 379.029 plus 253.9. 0.94 plus 0.1368, I get 1.0768f is equals to 379.029 plus 253.9, 632.929. Then you can divide everything by 1.0768, 1.0768. Your F becomes 587.8 newtons. And that is the force that will be required to pull the body up. Okay, so now let's try the second portion. So all of this is part A. Now let's try part B, where we are calculating the forces that will be required, or the force rather, that will be required to pull the body down. So remember the way we go about our equation: the forces applied on the body, we equate them to the forces that are resisting the movement that and they're trying to come up with. And this is trying to pull down, and this is trying to keep it. Okay, sharp. Then remember, what's trying to pull down, essentially we have lifted as the forces that are acting along the parallel plane with our surface. Our surface is inclined, so what's working on the parallel plane is our fx here, as well as our mg sine 15 here, They are acting in the same direction, so we add them together. Okay, so remember our fx is our f cos 20 plus our mg sine 15. Remember they're in the same plane and in the same direction. Now we're trying to express this, and remember it is made up of your perpendicular forces, sorry, times your coefficient of friction. So now we open our one big bracket. Which forces are perpendicular to the surface that we're acting on? And remember that our surface is at an incline. So first we have our mg cos 15, and then we have our f sine of 20. They're acting in two different directions. We can choose which one would like to be positive and which one would like to be negative. In an instance where you choose f sine of 20 as your positive and your mg cos of 15 as your negative, all this means is after you've calculated, you'll most likely get an answer in negative, and this will essentially tell you that the assumed direction is the opposite of the correct one. That's all it means. It doesn't mean your answer is wrong. So I like to appoint whatever is due to gravity as the positive. So we have our mg cos 15 minus our f sine 20 multiplied by our coefficient of friction, which is 0.4. Okay, then from this point on, you can try to break it down further or simplify it before you break it down. It really is up to you. Cos of 20 is 0.94f plus sine 15 was 0.259. Oh, there's mg happening over there. Not me confusing myself for no reason. 9.81 sine 15. Then on this side we have the same situation. 100 times 9.81 cos 15 minus sine 20 becomes 0.34 f times 0.4. Okay, then now we just simplifying it even further, plus you can just punch it into your calculator exactly as you see it, just so you don't, confuse yourself with all the numbers. 253.9. Then on this side we have same setup, it's just with a cosine. 947.573 minus 0.34 f times 0.4. Then you can move all the f's to one side and all the numbers to one side. So on here I have 0.94 f. Since that was a negative, it becomes plus 0.1368 f. On this side you had 379.029, then minus 253.9. On here you just need to be very careful with your numbers. I think that is the only tricky part with here. You may get confused with all the negatives that are crossing over and all the numbers that are multiplying each other, but just make sure that you pay special attention to that. It's very easy to have the right concept but mess it up because of the numbers and because of the signs. Okay, so those ones are subtracting, then you end up dividing by that and that. Then your f becomes divided by 1.0768. You get 116.204 newtons. and that is the force that will be required essentially to pull the body down, whereas this is the force that will be required to pull the body up. Okay, let me just try to put it in such a way that everything will be visible. I just don't know if it's possible. And I've realized I have just this thing about me. I cannot for the love of me write straight if there are no lines. But that's essentially how you'd go about solving it. I hope this is clear, but if it happens that any bit is confusing, because I'm aware that we had a bit of a run around, if anything is a bit unclear, please and please, please don't be shy to get hold of me. All right, I'll wait to hear.